Good afternoon and welcome to another version or another session of our biomechanics outreach. Today we are going to conduct a virtual tour of the Marshall Biomechanics Labs hidden away in the Henderson Center. As you enter into the room, one of the first things that you will see are the cameras on the back wall that are part of our 3D motion capture system. They are Vicon Vantage 5s that operate in conjunction with the Vicon Nexus system. What we do with this is we capture human movement and eventually process it and analyze it to be able to determine joint velocities, joint angles, accelerations within, if we use some other devices that help to extrapolate that kind of information. You have all seen 3D motion capture in some of your sci-fi movies and even your gaming, but it's the same technology, but the manner in which we capture data is significantly different than the individuals who do gaming and CGI for major motion picture. Our end product obviously is not as highly refined and such, but the reliability of what we get out of the system is high quality. The cameras are very unique in the fact that these cameras capture up to 450 frames per second. That is significantly more than what, say, your iPhone or most camera, off-the-shelf type camera, DSL type cameras pick up. Usually it's 30 frames per second, up to 60 frames per second for those type of cameras. The other interesting thing is that as you take a look at that camera, you can kind of see a ring of LED lights that are sitting back in there. Those are infrared, and what those infrared markers are specifically designed to do is to pick up retroreflective markers that we apply to various body parts. So things that we use this for in our lab, we obviously do a lot of human-based movement research. So I'll turn it over to Dr. Lee and let him describe what he's up to.
So we have a subject here, and I'm going to set everything up. There's some reflective markers that are already attached, and I'm going to attach some more just to kind of show you how it's done. We're going to build a 3D model based on those markers. So these reflective markers here, I attach them using double-sided tape, and I need to do that on very specific landmarks. If you come stand here next to that. Okay, so what I'm looking for, I've already marked up specific anatomical locations like the ASAS on the hips. I've marked up on the torso. I've got onto the right side is done already. So now I'm going to put markers onto the left side here. So I'm looking to find the femoral epicondyles. And I'm just literally just sticking these markers, which are, it's plastic as a base with polystyrene, and then it's covered with a reflective tape. And that reflective tape is what allows the infrared from the camera to hit the reflective marker and then bounce back directly. So I just put these on the specific areas of interest, looking for the femoral condyles. And if I can find the femoral epicondyles, that gives us the joint center. I'm also going to do the ankle joint center and find the two malleoli. So that line between those two bony landmarks gives us the location of the ankle joint.
Can we get the camera repositioned so that it's on your subject a little bit so that we can see actually what you're doing?
Is that better?
Yeah.
Okay. So I've attached markers to the condyles of the knee, to the malleoli of the ankle, and here, which is just on the front of the tibia. This gives us a direct line between the knee joint center and the ankle joint center. But the problem with these markers is, especially on a day like today when it's pretty warm down in the lab, these markers are likely to fall off. So what I'm going to do is I'm going to get some pre-wrap, cover them in pre-wrap, make sure that they really stick, because if the marker comes off, it's very difficult for us to be able to get that back in exactly the same place, and we've invalidated our data.
Okay, so we'll take time. What have you guys, our graduate students, used this system for during your time at Marshall, and and when did you start using it? Very quickly.
Okay. Yeah. So, with grad school, we haven't really used it so much for research yet. I think we're getting to that point. But one of the things you do with both undergrad and grad is you do research projects for the classes that you have, and with those, you get down in the labs and you work on stuff with these. For that, we've done reaching tasks, jumping tasks. What else have we done so far with this?
Did we do any jumping?
We did jumping.
Done a little bit of running as well.
Oh yeah, running.
You guys did. Well, that's force plate. Did with the iPads research.
Yeah, you all did that, Jeremy, right?
Yeah, that was really cool. We got to kind of see how the body stand, like people balancing on one foot, and then also balancing with on like one of those squishy foam pads as well.
Basically, we did some best testing, which is to assess concussion status and return to play following concussion. That to just rely to investigate the reliability of an app that's based on an iPad, placed in the small of the back, and how it affects motion.
Bill, you did some stuff with the punching right for your capstone. Maybe you could explain about that.
Sure. So this used the force plates and EMG, and if anyone saw the football tackling dummy in the back earlier, that's also a part of it. So the motion capture. So what I would have each of them do is I would have each subject punch the bag with your wrist in a specific orientation. I'd have it vertical, horizontal, and also what I call 3/4, which is somewhere in between. So I would have them punch the tackling dummy while I was on the force plates with one of those. Well, they would do all three eventually, but they would do them one at a time in a random order. So to determine, like, by changing that one thing, the wrist orientation, it changes the kinematics, the movement. So how the force transfers through the forearm should be different. And with inverse kinematics, we can use the movement and the force generated from the punch to kind of calculate how the force is transferred through the body.
Okay, so the subject is now has the markers on. So what I'm going to do is I'm going to do a screen share of what it looks like in Vicon Nexus to be able to see the markers, and I'll also put this camera on the subject so you can see what it looks like for the markers and then what it looks like through the software.
So one of the unique things about the biomechanics program here at Marshall is that, like Nick and Jeremy and Bill can attest, that students are introduced to this equipment very early within their studies here. Their first class, HS 465, which assesses, which is biomechanical movement analysis, they start being introduced to the systems through some of the activities that they do in class. What you see here in front of you is the grid in, that the Vicon system displays when the system is up and operating. You see that 3D field. You can get the depth and the width from the grid below, and then you can see the camera number 4 up at the top, and so you can see how we can see the three-dimensional piece. You saw the subject walk into the arena or the environment, and you can see the markers that have been placed upon them.
And if you can see the camera view, you should be able to see the subject with the markers just standing on the force plate. Okay, so what I'm going to ask the subject to do is go back against the wall. And I'll say 3, 2, 1, and then just walk all the way through the room. So I'll do this first. So if you watch the Vicon Nexus screen, you should see the markers appear on the screen and track across the force plate. And then I'll switch over to the camera and then go backwards and forwards, and you can see what we're seeing in the lab and what we're seeing in the software. So 3, 2, 1, walk across the room. And you see the subject appear and then get out of the volume again.
One of the unique things about this system is that we have to tell it and help it define the volume that the subject moves in, and so we calibrate the space prior to the subject being introduced to the environment. And once the system knows where its space is and such, the ability to calculate the parameters that we're looking for is very simple once the system understands the space.
And so now I'm going to have the subject do exactly the same thing, but I'll follow with the video camera. So you'll see what it looks like to us in the lab, and then I'll do it again and play it back in the software. So you should get an understanding of how small the markers are, how much they do not interfere with movement as the person's walking. Okay.
All right.
And then I'll turn the screen capture back on. Okay, and walk across the...
Okay.
So hopefully everybody was able to see the subject moving with the markers and saw the screen capture icon of what it looked like with just those reflective markers showing up in the software. So what we have here is a stack of lower extremity marker set. There are markers on the subject's feet, one on the great toe, one on the little toe, and one on the heel on both sides, and then one on medial and lateral ankle. They're going up 2 on each of the tibia, 2 on each of the knees, and then on the thighs at the greater trochanter, on the hips at the right of the SIS, and then just at the top onto the acromion. And so that set of markers is a standard lower extremity marker set that we can use to reconstruct joint angles of the hip, the knee, and the ankle. And if I switch over to the software again, so you can identify those markers within the framework. Could you just step off the? Yeah. So you can identify. So she picks up her right leg. Face me. Pick up your right leg. Yeah. And then put it back down again. And then left leg. And then back down again. What we're seeing in the lab is mirrored within the software, and all we're seeing is the representation in 3D space of those markers. I can spin this around, I can look from the side, from behind, from above, so everything is in complete 3D.